Okay, so as you can see, this is one of the paper which I wrote down when I was a student, um, or probably PhD student at that time. And then I have a few more papers, but I just want to show you this paper. This is related with the vibration analysis, and I wrote down the theory section. So I'm gonna give you this paper today to share with you that you can select your project as a group of three students. Three students will be co-author, and I will be monitoring your progress throughout the semester. So I will be the kind of co-author at the end of, like, usually mentors. They help you to review your written transcript manuscripts. So that's how we give credit to the mentors, which is usually this was my PhD advisor Karim G Sabra. So I wrote down this paper, so he guided me uh, what theory you should find out and how can you. So this is the format, so you can see. I think this length is good enough. Like, this is about around 10 pages long. So, and if you what we call the references. So now the thing is, you have to select your team members, or I think for the online students, I can give them the opportunity this week. They can make their own group of three students who will work on the project throughout the semester. You will submit at the end of the semester, maybe the second last week of the semester. So this paper will be, I think it will be in a good shape. So any other questions or concerns? Do you want me to share with you some projects, or would you also, I will suggest I will share what I have, and you will also look for what your interest is. It could be sound related project, because sound is all vibration. You see, when music plays, the vibration happens, and the walls or the glass, they vibrate. The air vibrates, and it vibrates our eardrum. So it could be sound related, or it could be muscles related. But right now you have plenty of time. I'm alluding it to you in the beginning of the semester, so that you should not, like, you will not have a small amount of time to finish this project. So the next week you will have to come up with at least three different ideas, and I will select what you can do with those three different ideas. And give me, in one idea, give me some, uh, like, the background. Why are you interested? And some people have done work in this area, and how is your work going to modify the old work? That is sufficient for me to understand. So, and this is more of a MATLAB programming. You will find the results through the coding in MATLAB and do the research. You may not have any chance to do the experimental work in on campus, because it will take probably too much time. But it is better to stay home and do some coding, do some like MATLAB programming in terms of, like, suppose natural frequency of a structure. So you just plug in the mass, which is maybe 10 kilogram beam, and the damping is this much, and the stiffness is this much. This is a natural frequency. So you have to give a thought process. So I will look into this and I will help you out. So my help would be that the paper which you will write down, it should be published to some forum, eh, at least our Kennesaw State research journals. They, your paper should look like that is acceptable, or the regional conferences, Like usually we, my directed study students, they presented at Georgia Tech conference, which is not very like a highly like a sophisticated conference, so they can still publish papers at that conference, IEEE. Okay, so any questions so far? You guys are good? Yes. Yeah, research paper or design related paper, because the experiment, and without the experiment, or maybe some students they have the experimental data, they work somewhere, this happened in the past. So I'm quite open, whether if you have some research work done, you have done some you have found some data which you want to process in MATLAB is easy for students to produce some findings. So if it is eardrum related and you want to design something like noise reduction device, it's up to you. I cannot like, I may give you some ideas during the week, but it is better that you come up with some ideas. With first of all, under this week task, make a team and find three ideas. Maybe a joint efforts. I would suggest joint effort, because this is higher level class, not undergraduate. So you'll come up with a decent idea which is related with your master class. So I believe it is 15%. Let me check the percentage. The in the I think in the syllabus I have said that this is 15% of your overall grades. So usually students get like quite close to 15% in this project, in my past experience. So they feel easy to get 15% out of the final project as compared to final exam and other tests. So it's kind of grade booster, I would say, because you start working from the beginning with my help. I will mentor, I will supervise you. This week you will come up with ideas. The next week you will write down an introduction. Third week you will start writing down the MATLAB code or finding the data. Or 2 weeks time, you if you need more time in results, because most time you spend on the experiment like MATLAB programming, and some people bring that 3D prints. It depends what kind of project it is. So okay, so let me show you the, so any question from the online students? You guys are good? Think that. Let me check. Okay, that's good. So I also uploaded the first lecture on YouTube. Were you able to see the link? So this lecture I will also post on YouTube, because probably finding a link in MS Teams had been difficult for the students in the past. So I would say just download it from the link, upload it on YouTube. I have made some more videos on YouTube channel regarding the whole class in the past. So you can watch that when you have spare time, just go through that, what, just to get a taste. I would suggest you can go through small videos slowly. You don't have to, like, if I'm doing chapter 1, you don't have to go to chapter 5 to start watching. It might be rusty when you start reaching at that stage. So I would say just one lecture ahead of what where we are right now. So right now we are doing the chapter 1. We will finish it today, and I will start chapter 3. Dynamics portion is related with more of the chapter 2, but if I need, we will solve chapter 2 later down the road, but I'm gonna skip for the moment and start chapter 3 right after this chapter 1. And there is a quiz, And other thing important thing for the online in-class students, your quiz and test will be the same time on Saturdays, starting from 7 a.m. till 1 p.m. That's the to be like consistency with the other students. If they are using open book, you should be allowed to use the open book and forms. So I want to give you the fair like opportunities. So this is the meeting time for lectures. And if I need to make some more video lecture during the week, I can make an upload on the YouTube. Right now, I think there are sufficient YouTube videos. Plus, it's a master class. You will study on your own some of the textbook theory to complete your problems. You guys are understanding what? Okay. So three people per team is good, right? Three students per research team, correct? Two is quite like small. I think three is good. And now description of vibrational motion section 1.2. I skipped that portion last time, so let me show you what it is. It is, please write down this uh, equation of simple harmonic motion. Students are asking where to, yeah, I'll open the Dropbox for the and homework today, and you should be able to upload it over there. Thank you, Jared. Okay, now let's go to the theory behind this simple harmonic motion. Why is it important? I will tell you in a bit. It is very important to understand the simple harmonic motion, and the simple harmonic motion looks like this shape. When we plot it on the time axis, our x-axis is time axis. Look, this axis is time axis, and you will see. So you see omega equals to 2 pi f, and f in terms is the cycles per second. How many cycles per second? Omega equals to the natural frequency, or I would say another term is radian frequency, like how many radians um, it is moving with per second, radians per second. And if I say the time period, in our book, the time period is the letter P. You see, time period is P. So time period is 1 over F. So from here, so can I write down like this? 1 over F. So let me rewrite here. I'm so that you should not get confused. So F equals to 2 pi over omega from this equation. I would say from this, correct? And now from here, I've reciprocal of this is, that means 1 over F equals to omega over 2 pi. I'm sorry, this is, I'm writing down So let me show you what I mean by that. Omega equals to 2 pi f, and f equals to omega over 2 pi, correct? And time period, it is reciprocal of uh, frequency. So can I write down like this, 2 pi over omega? This is the same thing. Time period is the time between the two uh, consecutive points in in a cycle. Two consecutive cycles, you pick two consecutive cycles, and usually the maximum points is easy to identify. There's a maximum, so peak to peak distance is the time period. And okay, in one vibration the time period is, it completes its one sine wave, completes its one vibration a, from 0 to pi and 2 pi. It starts repeating its cycle. The sine wave, cosine wave, what is the time period? 2 pi, like 360 degree. If I draw a circle, so if I draw a circle for you, so you will see. So if I draw a circle, then it will if the point is marked here, the point starts going up. This is our, we call it as a phase angle. So this, if this is starting from here, so you will I should redraw it here, so that in order to match this over here. Okay, now this is our angle, phase angle, and the point is here. Over here, pi by 2 radians. So the point is, maximum amplitude is over here. The mass or vibrating object is at pi by 2 and divided by 2. You see, why am I dividing by 2? But divided by omega. Why? Because 2 pi is the time period of a complete wave. But right now it is pi by 2 divided by omega. That time period, omega is suppose 1 radian per second, suppose. Then pi by 2 is the time in terms of radians, so I will say time period. You see my point? So that's why it is done pi by 2, pi by 2. Omega is coming like over here, so similarly you will divide by omega. You see my point? So this x is our time axis, agreed? And this is the amplitude. This is how you read the frequency, the sinusoidal pattern. This is a simple harmonic motion. So another thing I want to mention, that if you take the time derivative, if you take the time derivative of this displacement, you will get velocity. And so let me explain to you this one. This is starting from here exactly without phase angle. If phase angle is 0, the sine wave will start right at 0 angle. So a sine omega t plus 0 means it will start right from the 0 radians frequency, or 0 degrees. Both are correct. But if it is starting, if you want to trace it from here, so you will trace this point, and then you will see. So it is leading by a certain phase angle, which is phi over here. So usually put this over here, if there is a phase difference, it is not exactly starting from 0 degree. The particle is away from 0, so you will count that into your uh, formula argument. And you see, cosine comes right after 90 degree. Look over here, let me show you. Over here, this was the description of the sine wave. Now I want to show you that if you want to plot, let me redraw it here. So if you want to plot the for cosine wave, you will start from here. amplitude. So it is, the angle is pi by 2 radians. You see the if this is if you add pi by 2 radians into this sine wave, you will get cosine wave. They are out of phase by pi by 2 radians. Sine and cosine, they are out of phase by pi by 2 radians. So this is how you write it down. And if you draw the sine, cosine, and if you draw y, which is the displacement or the position, and the dy over dt is the velocity, which is over here. This is our velocity, this is our acceleration. So they are out of phase by, our velocity is out of phase by. So this is my acceleration. Sorry, this is the position. This is our velocity, this is our acceleration, this is our displacement. This is not exactly starting from zero because of the, as I mentioned, this was having some phase lead, which is phi or phi. So this is out of phase. Usually it should start from here, but it should start from here, but it is out of phase by 92. That's why we have cosine angle, cosine or sine pi by 2. So that was the thing which I wanted to mention. Now I want to talk about this simple harmonic motion, which is not undamped but damped due to some damping. You see this exponential, we call this exponential decay. When you multiply this by a sine wave and amplitude is, so this is known as the damped simple harmonic motion. I would say, how is it dampening out with this envelope? So let me show you. So over here, so if you have a mass, a spring, a damper, so if you want to plot it, it will be like mx double dot equals to minus cx dot. Imagine this is moving upward, minus kx. So if you lift this up and leave it like this, it will start oscillating. So this is standard form. This is the actual differential equation of motion. And if you compare it with the standard form, so this is a standard second order differential equation of motion. So if you compare one with two, So we can find out the natural frequency if we compare the coefficients x. What is the coefficient on the left? Equation 1, equation 2. Equation 1, this is coefficient is k over m. It is equal to omega n square. So we found that omega n square equals to, sorry, this omega n equals to k over m, square root k over m. This is the natural frequency, or we call it as a resonance, free vibration. When you hear the word natural, it means it is moving freely without any force uh, being applied on it. So if this is just a mass spring system, it will be like undamped. But if it is a damper included, it will be an envelope that it will try to bring the oscillation down to zero after time, maybe like 4 times the time of infinity. So for example, it starts from here. So what is e to the like infinity? That is equal to e 1 over e to the infinity, which is 1 over infinity, it is equal to 0. So after time goes to t, this t, if this t, like if time goes to or infinity, I would say just time goes to infinity like this. If time goes to infinity, then the moving mass will come to rest. That's what the uh, decaying exponential means. And if you compare the velocity coefficients, equation number one is c over m. So this is 2 zeta. Zeta is the damping ratio. What damping ratio means? Actual damping divided by the critical damping. This is my actual damping. The damping coefficient of this damper is, this is the actual damper, actual C. And now the critical C is 2m. I would say critical C is written as 2m omega n. So I can find out C over 2m omega n, which is the damping ratio. Okay, and omega n, if you do the math here, C over 2, you can further simplify. This is k over m C over 2 mk. Please note it down. Now I want to teach you one concept here, which is the time constant. So you see the oscillation is going to zero because of the damping. That's what it shows me, because of the damping. And you want to find out what is the time constant here. This is time constant, yes. Oh, this is an important term, time constant um, of a vibrating system. For example, you have a equation of differential equation, like first order. I would say time constant x dot plus x equal to 0. So x equals to, how this how are you getting this answer? This is our solution of the differential. At any time, you can trace the displacement. This is at any time dependent. So I will rewrite it now. This is the general solution. So this solution, it comes from here, and I will explain you. This the oscillating solution of the differential equation. There are multiple ways, but the major thing is that what happens, what if time constant, if this time equals to time constant, what is the, like, this is our graph. It looks like this graph. So suppose this is our oscillating amplitude, this envelope, and this is going down. So if t equals to c, time constant, what will happen to this? So e to the negative 1 equals to 0.37. You can check it. So if I do the math, that if t equals to the time constant is in seconds, correct? So exponent negative 1, it is about 0.37 decade. Initially, suppose it started its position at a certain x0, maybe it could be equal to a amplitude. Okay, then it starts decaying its amplitude when it reaches a certain time, like time constant over here. So it has gone down to 37 or 0.37 of the starting initial condition, starting value, which is a amplitude. And what if we go to the exponent negative 4, like 4 times the time constant? You will see it has gone down to 2%. very small. So if you want to double check it, it's about 0.018 multiplied by 100 will be like 2%, almost 2% left from the original starting initial condition. So if I go to 0.5, so you can see, sorry, if I go to the negative 5, is about 0.67. So this is what has been described here, that I would just copy the whole thing here. You see, first time constant, it hits 37% of the original starting initial condition, and the 4-time constant, it goes to 0.02. 5 times the time constant, it goes to 0. And this looks like this behavior. And the oscillation keeps on going inside this curve. They are starting decaying. If you multiply this e to the negative t over tau with sine wave, the sine wave will start becoming amplitude will slow down and will come to rest. You see my point, guys? So let's do one problem here. I want to show you one problem. Oh, let me check it. I think I have the problems here. Please note it down. A particular function has a form so y of 1, it is 4.912. Y at 3 seconds is 3.293. So compute the values of a and tau. So you have two equations, two unknowns, correct? So y at time t equals to 1 second, it is 4.912. That is a e to the t over t is equal to 1, correct? Right now it is 1 second. And this is equation 1. And for y equals to 3 seconds, this is 3.2. Okay, 3.293 a to the negative 3 over tau. So if you divide both, divide 1 and 2. So if you do the math, you should get tau, which is the time constant, equals to 5 seconds. You can verify it.
Does tau have units?
Uh, tau is time constant, so it's like seconds. It could be millisecond or some other. They have not specified it.
Okay.
Do you get five value or 5 seconds? Yes,
Yes, 5.
that's good. Okay, now after you plug in 5 here, so then what you have to do here, so y equals to a e to the negative t over tau. So for example, at 1, it is equal to 4.912. So can you find out amplitude from here? I believe it should be 6, but you can double check this answer.
And that's what I got.
So students has verified it. That's good. So any question? It's just a basic maths. So I believe you can easily solve this at home. So let's do one more problem. So the question is, if you were to sketch the plot of the function t over 3, so what would be the appropriate ranges for y and t? So y starting from like when time t equals to 0, okay? And we are interested as 4 times the time constant. As I mentioned, we don't go to keep waiting until 5 times the time constant. We just try to analyze that how much time would our system take to decay to like 2%. So what I suggest, like 4 times the time constant would be our the range, which is the last limit of our complete to show the complete picture of oscillations. So what is the time constant looking at this plot, the equation t over tau? What is tau in this denominator, the exponent in the denominator? It is 3, correct? So tau equals to 3 and t equals to 12. You see my point? So, and you when you plug in 0 in over here, you get like, so here you will get, it starts from 0 to 7 infinity. So I think, let me double check, it is -7. Yeah, I have to put -7 here. Sorry, this is when time t equal to 0, y is equal to 7. I will say when time t equals to 0, it is starting from 0. Maximum time is 0. Like it looks like this plot. After all, it will go down to 0, like time 4 times the time constant, starting from the maximum value, which is 7. Let's do another problem. If you were to sketch the plot for this function, what would be the appropriate ranges for y and t? So y, you can, so well, like for the time starts from 0, you will pick up the maximum time constant. Look, this is the maximum tau 1. Suppose this is for tau 1, which is 2, tau 2 equals to 5, correct? And we have to multiply these tau by 4. Okay, so starting from 0 to 20, so it will completely show us the picture of the oscillation 4 times the time cost, and that y will start from 6 plus 12, 18. I will say maybe 18. Starting from, let's start from smaller number, so it will show you from 0 to 18. So this is our one line question. Let's do another problem here. A particular motor rotates at 3000 RPMs. So number of revolutions for this motor, 3000 RPM. What is the speed in radians per second? So omega equals to 2 pi n. This is in radians per minute, but divided by 60 gives you radians per second. And then it is asking you how many seconds does it take to make one revolution? Like time period. Time to complete one revolution is the time period. And time period equals to 2 pi over omega. So omega from here you will get 314 radians per second. When you plug it in over here, you will get 0.02 seconds. Can you verify this?
Yes. 100 pi rads a second and 1/50th per period.
Okay, that's good. Let's do one more problem here. These are the basic problems. I'm gonna start few more problems soon, but I want to start from the basics first. So the question is, the displacement of a certain object is given by this expression where t is in seconds, and compute the time period and its oscillation frequency. Oscillation frequency, I would say, written by F, and this is oscillation frequency, and the other radian frequency is written by omega. How many radians per second the particle is oscillating at. So now this is in hertz, and F equals to 1 over the time period. Time period is 2 pi over omega, or omega over 2 pi is F, correct? So, now the question is compute the time period. So I'm gonna show you the time period is 2 pi over omega. Omega from here, it is written in the argument of the sign, which is 5. Omega equals to 5 radians per second. So what is the time period? It is 1.257 seconds. This is the time period of this oscillation. And the other thing is the oscillation frequency is 1 over time period is 0.796 hertz. You got this point correct? Okay, let's go to the next question. What values must be B and C have the for the following to be true? So we have to find out the values B and C. So this is a trig identity. If you remember, sine alpha plus beta equals to sine alpha cosine beta plus cosine alpha sine beta. So we can split it up. We can split up 10 sine, like alpha is in place of alpha, it is written 3t. In place of beta, it is written as like 2. So 10 is outside the parentheses. Sine 3t cosine 2 plus cosine 3t sine 2. And then if you do so, if you just open it up, so you will see, I will say b in plus, I can write on just b, whatever coefficient it is with this one, the this everything is outside. This is the coefficient, and 10 sine 2, the coefficient of cosine 3t. This is c. This is I will say, let me rewrite here for your convenience. Over here, this is 10 cosine 2. This is b. So b equals to, is it true? I think my calculator is not reading it. Okay, let me double check. Cosine 2 in radians. Yes, this is correct. Now the other one is in degrees, which we, this should be in radians units. So b equals to 4, -4.16, -4.16. What happened? And c equals to, and no, 10 times cosine 2, sine 2, sorry, this is not 9.093. You got my point, guys? Have you guys understood how did I solve this trig identity question? So let's do one more problem similar to this one. what values of a and phi uh, have for the following to be true. So what you have to do, you have to use the trig identity and do this like a sine 60 plus phi equals to a sine alpha cosine phi cosine alpha plus sine phi. Sorry, not plus. It is other than the this everything is coefficient. So a cosine phi is the coefficient of sine 60, correct? And cosine 60, the coefficient is a sine phi, correct? So we know from the expression a cosine phi equals to negative 6.062 and a sine phi equals to, it should be plus negative 3.5. You agree with your professor? So sine and cosine, they are negative, they are in the third quadrant. So this is the third quadrant, like pi, this is phi. So I will say phi is equal to tangent inverse sine of sin 3.5 over 6.062. And if you want to find out the total angle, you will add this. Yes, this is total phi. I will say this is what we call angle phi. Let me check.
Minus 3.5.
Yeah, minus plus phi. Actually, this is, yeah. So total is this angle. So we have to add this whole, I believe this minus, starting from zero axis, positive real axis. So this is the phi angle. You have to add this pi. What is a? If you do the math here for a, let's do one thing. A cosine phi equals to negative 6.062 equal to 7.
I got phi is pi over 6 plus n pi for any
So,
value of n.
so
Any
you
in,
did you add the fee you are getting is, I believe, correct, but we have to take it from the positive real axis. Add pi into this.
but I thought phi could be uh, any integer of n pi plus pi over 6.
It is now at the in the third quadrant, correct?
That's when, yes, when n equals 1, it's 7 6 pi, which is what that is. Um, but phi could be any integer of n, I thought.
Mm. So you see the cosine phi is negative, sine phi is negative, so they are in third quadrant. I believe that's what it is.
Gotcha.
So let's do one more problem. We have some time left. Let's do this one, 114. The question is, as measured by an accelerometer, the amplitude of acceleration of a vibrating object is zero point 0.7 g. So the amplitude of acceleration of a certain vibrating object was zero point 0.7 g with a frequency 10 hertz. So omega equals to 2 pi f 20 pi radians per second. So amplitude of acceleration. Let me show you the uh, acceleration. So starting from y as the position of a simple harmonic motion, correct? So this is vibrating, as we know that object displacement velocity, compute the amplitude, the object displacement and velocity using the simple harmonic motion. Okay, now g is given. So that's the, what is the velocity formula? A omega cosine omega t. And what is the second derivative of position? It is negative a omega square sine omega t. So this complete is the amplitude. So amplitude of acceleration is whatever the coefficient of sine omega t is, that is the amplitude. So that is equal to 0.7 g. And from here you can find out amplitude, which is equal to 1 point, you can find out a, which is equal to 1.739 into 10 to the negative 3 meters. This is the amplitude of displacement. And if I ask you, okay guys, can you find out the amplitude of velocity? You will just multiply a with omega. I would say just magnitude, just positive value, like omega equals 2 pi, correct? Multiplied by 1.739 in 10 to the negative 3. It is about 0.11 meter per second. You got my point, guys? So this is how you will find out this one. Please note it down. So when you go home, you study this table that e to the x is in the Taylor series represented like this. And you can apply the same Taylor series to find out the cosine, like e to the theta. I would say e to the j theta equals to over here. So if you do the math, you will find out this is the Euler identity. This is all Euler identities, correct? That e to the j theta is the real function is cosine theta plus iota sine theta. So cosine theta can be written as in, I will say just 1 minus theta square over 2 factorial plus theta 4 over 4 factorial minus. And sine theta is theta minus theta cube over 3 factorial theta 5 over 5 factorial. So, but usually when we solve the problems, you will linearize um, the cosine angle. For small angle, you can linearize it up until 2 terms, and for sine theta, you can linearize it. I will solve one problem. and upload on a video for finding the differential equation of motion of a simple pendulum. Oh, let me show you this, the one which I just explained you. I'm gonna copy and paste here for your convenience. When you go home, you just read the theory that from the Taylor series, I have I have used the Euler identity in place of x. Look, Taylor series says any variable power x like e to the j theta. You can find out from here to e to the j theta, and from here you can find out this term. And all the real terms are the cosine theta. All the imaginary terms are the sine theta. That's how I wrote down these things. Correct? Yes. Table 1.4, the complex algebra, you will read this. I will make a small video for the simple pendulum, the differential equation of motion for that one. So you have a test, oh sorry, quiz on probably this Saturday, correct? Which will cover this chapter problems, homework problem. And I've given you quite a long time slots to open the quiz for 40 minutes. It might, yeah, you have to upload the solution on the D2L assignment Dropbox, correct? Okay, within the 40 minutes. When you open it, it will give you 40 minutes time slot, but you can open it from 7 a.m. to 1 p.m. Okay, just chapter one, the homework problems.